Hey folks, today we'll be introducing the concept of time series. This video is not very heavy on the math, but then again, neither is the exam, so we'll make sure to cover concepts that the SOA might test you on. Let's start by defining some terminology. Starting off, a stochastic process is an ordered sequence of random variables indexed by time or space. It is used to model systems or phenomena that evolve over time in a random manner. Let's say you flip a coin 10 times. The result of each flip is represented by a random variable. The sequence of the random variables is a stochastic process. Next, we have a time series, which is a sequence of data points recorded at regular time intervals. Capital T represents the number of observations, and each data point y is indexed in chronological order from 1 to t. So in the coin flip example, the results of your 10 flips could be represented by a time series, such as heads, tails, heads, tails, heads, tails, heads, 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 tails. Longitudinal data follows the same subject over time, such as a medical study that follows a group of patients over 10 years to observe the progression of a chronic disease. Cross-sectional data captures information across different subjects at a single point in time, such as collecting the weight, height, and blood pressure of a group of people at a single point in time. Panel data is a combination of longitudinal and cross-sectional data, where information about different subjects is observed over time. When looking at time series, we have to be careful about spurious relationships. Here we have two independent time series. Let's call them Series A and Series B. It may appear that one series is affecting the other, but this may not be the case. This is called a spurious relationship. Spurious relations are often caused by a third confounding variable that causes both series to move together. Another way to imagine this is to plot the values against each other in a scatter plot, where each value occurs at the same time. It looks like Series A and Series B are causally related, doesn't it? A nice positive correlation. But just because two things go up over time, it doesn't mean one causes the other. Correlation does not imply causation. Don't let them trends fool you. Here we have an equation that represents the relationship between two variables at the same point in time. Although this type of model is frequently used in regression analysis, it is not suitable for time series data. One major issue is that a model like this doesn't factor in the time trend for either variable, so we're not factoring the previous values to predict future values. Another concern is that this type of model might lead to a spurious relationship if both variables are trending in the same direction, which we discussed earlier. Imagine you're studying the relationship between advertising and sales. Suppose sales spike every December. Is it your brilliant ad campaign? No, it's just the holiday season and it happens every year. But how would you capture this pattern with a simple linear regression model? Or what if both ads and sales are going up just because the economy is growing? That's a false relationship induced by a time trend. Yep, you know it, a spurious relationship. Now, suppose we're trying to predict y at time t plus 1. All we need to do is know the future value of x at time t plus 1. Yeah, so unless x is a function of time, that's not going to happen. The fix? We use a lagged value of x. By using a lagged value, we can overcome this forecasting limitation to predict future outcomes. Before we move on, a quick note on causality. This list is directly from the source material, so it can easily show up on the exam. There are 3 conditions that must be met to establish causality. First, there has to be a statistical association between the variables. Second, time order. The cause must happen before the effect. And third, the elimination of alternative hypotheses or establishment of a formal causal mechanism. Now, the basics of forecasting. Forecasting is the method of predicting future values of a time series. To do that, we need to understand the ingredients inside the data. First up, we have trends. These reflect the long-term movements. Think of this as the general direction things are going. Trends don't necessarily have to be linear or smooth. For example, they can be quadratic, binary, or even have a regime-switching pattern. Next, we have seasonal patterns. These are periodic fluctuations that happen over and over. The example we used earlier of sales spiking every December is a seasonal pattern. And finally, noise. These represent random fluctuations in the data. We can combine these components in different ways. The most common is the additive model. Another approach is the multiplicative model, where the trend and seasonal components are multiplied together. If you have a purely multiplicative model, you can actually convert it to an additive one just by taking logarithms. Let's visualize this. Here is a plot of our time series. First, we start with the trend. Then we add the seasonality on top of that. And finally, we add the unpredictable noise. And there you have it. This is one example of how a time series could look. In future videos, we'll dive deeper into time series concepts and formulas to understand these components in more detail. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.